Let us discuss about the symmetry properties of the DFT. First, we assume that the input x of n and its DFT x of k are both complex valued. Then, we can express x of n as xr of n plus j times xi of n, xr being the real part, xi being the imaginary part. Similarly, x of k is represented as xr of k plus j times xi of k for the n ranging from 0 to n minus 1 and second equation with k between 0 to n minus 1. From the definition of the DFT, we know that the DFT equation x of k is given by equation number 3. Now, substituting the value of x of n in this particular equation. After substituting, the equation will look something like this. So the input now is xr of n plus j times xi of n multiplied with the exponent e power of minus j 2 pi by n kn. Using Euler's relation e power of j theta cos theta plus j sin theta. Substituting, the exponent term now becomes cos of 2 pi kn by capital N minus j sin 2 pi kn by capital N. So multiplying, it results in 4 different terms. We observe that 2 of the terms do not have j and 2 of the terms have j. Therefore, 2 of the terms contribute to the real part and 2 of the terms contribute to the imaginary part. Further, after separating out the real part and imaginary part, we observe that the equations for the real part of the DFT is given by the first summation as shown here. This summation is involving the product of xr of n, this is the real part, into cos of 2 pi kn by n plus the imaginary part into sine of 2 pi kn by n. We are aware that cos is an even quantity and sine is an odd value. We know that sine of minus theta is minus sine theta and cos of minus theta is cos theta. So, the equation number 6 is representing the imaginary part. Please be aware that the j term is not included here. So the imaginary component is given by the summation minus xr of n sine of 2 pi kn by n plus xi of n cos of 2 pi kn by n. So these two equations 5 and 6 can be used to compute the real part and the imaginary part of the DFT separately. Similarly, if we consider the IDFT equation given by x of n is equal to 1 by n times summation limits k is equal to 0 to n minus 1 x of k into wn to the power of minus kn. Substituting equation 2 in the above equation, this time we are going to substitute for x of k. Therefore, the real part xr of k plus j times xi of k will be the replacement. Here we multiplied with the exponent e power of j2 pi by n kn, which can be expanded as cos theta plus j sin theta. Now, similarly, we multiply and we obtain 4 terms. 2 of them do not have j, they are the real terms, and the terms with j are the imaginary terms. Therefore, this equation 7, when you compare it with equation 1, it provides you with the real part of the input and imaginary part of the input. Now, in the real part of the input, we have 1 by n times the summation. Inside the summation, xr of k cos 2 pi kn by n minus xi of k sin 2 pi kn by n. And in the imaginary part, we have xr of k into sine plus xi of k into cos. So the equations here both are structurally similar, but the arrangement of elements is changed slightly, and so is the sign. And important thing, we have to multiply by 1 by n if it's a IDFT. Let us now discuss about the various cases. In case 1, we assume that the input is a real valued sequence. We are aware that when the input x of n is real, the sequence exhibits conjugate symmetry, that is x of n minus k is equal to x conjugate of k. And the magnitude of that, when you apply the magnitude of x of n minus k is same as x of k, and the phase angle is angle of x of n minus k is equal to negative of angle of x of k. So this is the property exhibited by a real value sequence. Now since the value of the input is real, the imaginary part automatically becomes 0, and therefore x of n can be calculated simply on the basis of equation 8. So equation 9, the entire term is equal to 0, hence xr of n is sufficient to depict the signal called as x of n. For a sequence which is real and even, x of n is considered to be real and even. X of n is equal to x of capital N minus n as per the definition. That's the definition of circularly even. Then equation number 6 says that xi of k is equal to 0. So this is primarily because of the reason that it is real and even. Therefore, a component which has odd term, a component which has the odd term and imaginary term will not be present, since we are saying it is real and even. That's the reason why xi of k is equal to 0. So this can be observed by testing the equation xi of k So in xi of k, this term is odd, so it cannot be present, and this term is imaginary, so it is also not present. So the entire term, it becomes equal to 0. Therefore, the DFT equation reduces to x of k is equal to summation n between 0 to n minus 1 x of n cos 2 pi kn by n. The sine term will not be present due to the reason that we are considering only real and even part of the input. Now x of k here is definitely real valued and it is even. Since we already know that xi of k is equal to 0, the IDFT equation also reduces to x of n is equal to 1 by n times summation k between 0 to n minus 1 x of k cos of 2 pi kn divided by capital N. In the next case, we consider a sequence which is real and it is odd. If x of n is real and odd, then x of n equals negative of x of n minus n as per the definition of circularly odd. Then equation 5, the real part xr of k is equated to 0. And hence the expression for x of k is given by minus j times summation n is equal to 0 to n minus 1 x of n sine 2 pi kn divided by n. So since the term is real and odd, the real part is ignored and we have to take only the imaginary part. And in that we are supposed to take the term which is real and odd. So in the imaginary part, we do not include the j, but in totality when you are writing the number, to show that the term is complex, we have to introduce the j term also. So the result here is the sequence is purely imaginary, it doesn't have a real term, and it is odd because of the presence of sign. Now since xr of k is equal to 0, the IDFT equation also you get as x of n is equal to j times 1 by n summation k between 0 to n minus 1 x of k sine 2 pi kn divided by capital N. In case 4, we consider the sequence to be purely imaginary. If the sequence is purely imaginary, then x of n is given by j times xi of n. We are talking only about the imaginary part. Then equation 5 and 6, they reduce to xr of k is equal to summation n between 0 to n minus 1 xi of n sine 2 pi kn by n, and xi of k is equal to, so we are only considering the term which is imaginary, the real part is left out. Now if supposedly xr of k is odd and xi of k is even, what happens? If xi of n is even, see from the above equation we note that xr of k is odd due to the presence of sine and xi of k is even due to the presence of cos. If small xi of n, the input is even, see we said that it is imaginary, but again we have two cases here which is even and odd. Suppose it's imaginary and odd, so xi of n is even, then xr of k is equal to 0 and hence x of k is purely imaginary. Further, if xi of n is odd, then xi of k equals to 0 and hence x of k is said to be purely real. So in summary, the properties, symmetry properties of the two domains can be summarized as follows. First we express x of n as xr of n, which is a real part. In that we have even as well as odd. So two terms here. Similarly for imaginary we have to put the j. So xi of n stands for imaginary. In that also we have even and odd. Similarly for the DFT we can identify the even and odd part of the real term and even and odd part of the imaginary term. Now the result may be very simply stated as follows. If there is a real and even term in the input, you have a real and even term in the DFT. If we have real and odd term, then we have imaginary and odd term. If you have imaginary and even term, you will have an imaginary and even term. If you have imaginary and odd term, we will have a real and odd term. So this mapping describes all the symmetry properties that we just described. Once again, let's take a look at the entire working procedure. First express x of n in terms of real and imaginary, x of k in terms of real and imaginary. From the first consider the DFT equation. In this DFT equation, you're going to substitute the value of x of n which comes from equation number 1. After substitution, next the exponent which is e power of minus j2 pi kn by capital N, it can be expressed using Euler in terms of cos and sine. So multiplying and expanding, we get real and imaginary part. So you compare the equation 2 and 4 and you write the individual expression for xr of k and xi of k as shown. Here clearly you can identify which term is even and which is odd. So if cos is found, it is even, and if sine is there, it is odd. Similarly, we can see which input is real and which is imaginary. So depending on the cases, if there is no real term, we can eliminate the respective term. If there is no even term or odd term, you can eliminate the respective term. This is how you select for the various cases. Similarly, you can consider the IDFT equation and replace the value of x of k as given by equation 2. Therefore, xr of k plus j times x of k is the substitution. Once again, the exponent we are expressing in the form of cos theta plus j sin theta. Theta value is 2 pi kn by capital N. Then, expanding gives you 4 terms, 2 of them are real and 2 of them are imaginary. Once again, comparing with equation 1 and 7, we obtain the expression for xr of n and xi of n. And similar results as the previous case will be witnessed here also. Now, to consider the 4 different cases, we consider real value sequence. What happens in the case of real? We know that definitely the imaginary part is going to be equal to 0, and hence x of n is calculated only on the basis of equation 8. When it is real and even, we have seen the condition and we have seen what results. So we get x of k, which has the term x of n multiplied with cos 2 pi kn by n. So this is a real valued and even. For the IDFT, we have x of n is equal to 1 by n times summation x of k cos 2 pi kn by n. For real and odd sequence, we have seen the definition and we have seen the condition here. It results in a sequence which is purely imaginary as well as odd. For x of n also we have imaginary and we have the odd sign term. For a purely imaginary, we can eliminate the real part and the expression becomes xr of k is equal to this quantity and xi of k is equal to this quantity. So whenever you have sine, it is odd, and when you have cos, it is even. Therefore, xr of k is odd and xi of k is even. And if small xi of n is even, then xr of k is equated to 0. And if x of k, and hence x of k is purely imaginary. If xi of n is odd, then xi of k is equal to 0 and x of k then becomes purely real. And we have summarized all the properties that we have just studied. Let us now consider a few numericals based on the endpoint DFT. The problem here given is to find the 5-point DFT of the sequence x of n, which is 1, 1, 1. Please note that the sequence is of length 3, but they are asking 5 points. This is possible. You may be given sequence of any length and you may be asked to calculate DFT for a certain number of points. So suppose the length of sequence is less, you can pad sufficient number of zeros to make it length n and then proceed for the calculation. So here in this example, from the definition of the DFT, we are aware that DFT of x of n is given as x of k, which is summation n is equal to 0 to n minus 1 x of n w into the power of k, with k value lying between 0 to n minus 1. Now in the problem, the n value is provided, it's equal to 5. Substituting the value of n in the above equation, we get x of k is equal to n between 0 to 4, x of n into w5 to the power of kn, and it has to be solved for k value ranging from 0 to n minus 1, which is equal to 4. Expanding the summation gives you the sequence which has real factors powers in terms of k. Substituting the value of the input x of 0, x of 1, x of 2, which is given as 1, 1, 1, and the remaining terms are 0. So the last two terms, they vanish, and this is what you are left with after substituting the inputs. And this equation has to be solved for k value between 0 to 4. Now we need to determine the real factors first. For a problem which is based on n is equal to 5, we can compute the real factors by using the relation Wn is equal to e power of j2 pi by n. and then calculating the various powers. Therefore, for n is equal to 5, we require the first 5 twiddle factor powers, that is w5 to the power of 0, w5 to the power of 1, w5 to the power of 2, w5 to the power of 3, and w5 to the power of 4. We know that w5 to the power of 0, anything to the power of 0 is 1. w5 to the power of 1 is simply e power of minus j 2 pi by 5. Substituting, and you can get the answer in complex form. In the calculator, you can simply perform what is called as polar to rectangular conversion. To compute the square, we have to take whole square, so the expression becomes e power of minus j 4 pi by 5, and the resultant simplification gives you the answer as shown. Similarly, the next twiddle factor you have, w5 to the power of 3, is equal to this. Now we observe that there is a pattern here also. So the twiddle factors, they are exhibiting conjugate symmetry. So after the first value 1, the value 0.3090 minus j 0.95, you can see that here we have the complex conjugate of it. And these two are complex conjugate of each other. So you can save some time in doing the computation of twiddle factor powers. Now we can substitute the values in the above equation and compute for the different case, that is k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, and k is equal to 4, and we get the various answers. Here also you should observe that there is some sort of symmetry which exists between these values. So since the input is real, we can use the symmetry property and easily we can relate the term x of 1 with x of 4. These two are complex conjugate of each other. So calculating x of 1, we can easily find the answer for x of 4. Similarly, calculating x of 2, we can easily find the answer for x of 3. Finally, writing the sequence in the form as shown here, we are expressing the answer, the result of computation, as follows.
Thank you all.